Okay, so we continue. Remember, annealing is a heating close to the melting point, more or less 80% of the melting point, and then a slowly cooling. First the heating and then the slowly cooling. We can have several stages, but what identifies the annealing is a slowly cooling. And slowly cooling, it happens in minutes, hours, or days. And the tempering is a faster, very faster cooling. The faster cooling is called quenching. In quenching, we have to crystallize the initial structure into small grains. Well, to analyze the phase diagrams, for example here for steel, it's necessary to understand some regions on the phase diagram. A phase diagram, usually a binary, we also have tertiary and others, but to understand the steel and other metals it's common to use a binary diagram. In the left and right side of the x-axis we have the composition. For steel, carbon and iron. And in the y-axis, temperature. Usually on one side the lines touch the melting point of one of the components, and moving along the crystallization or solidification line, on the opposite side we touch the melting point of the other metal. For that case, 1500 Celsius is the temperature for iron. In the other side is the melting function for carbon. In this diagram, the lower point that separates liquid from solid is the eutectic point. Eutectic point is a place where the structure is the stronger because the material crystallizes like a sandwich. So layer after layer is like a muscle that reinforces the structure of the material. But not always is possible to work on the eutectic. For example, here 4% exceed the solubility of carbon in iron, and the material segregate. Remember the example of satanic students inside the holy people. If the material segregates, different phases don't help to the material to be strong, tough, or hard. It's a fragile material. So it's common to work in concentration where is possible the solubility. So here in 0.6, 0.8% of carbon, it's possible to work the material. The steel, when after solidification, create the first structure austenite or gamma. The austenite is the crystalline phase that holds the steel over 1000 Celsius, and after cooling the material reorganizes and pass to others: perlite, ferrite, spheroidite, martensite, and cementite. Cementite is a mixture of perlite and ferrite, but what's important for us is the conversion of austenite into others. How? Following a quenching or doing an annealing. If you select the composition, you always maintain this composition. Only change the crystalline structure. So at the same composition, for example, austenite passed to perlite at 0.8% of carbon and in a cooling like the annealing. But if you do a cooling in a different way, you modify the composition of the phases. This is an example of the cooling when you are placed in the eutectoid. So the material is a mixture of liquid and solid. These clear spaces is the material without solidification, and this line, these fibers, is the material in solidification. So passing from A, B, C, D, and so on, the material crystallizes. The grain is formed, increase, and some phases appear. For example, the gray or the dark are different phases, very different phases. Austenite pass to martensite or pass to another structures. For example, here the difference in color by reflectance of the light in metallography led us to follow the existence of these phases. In metallography, we also can understand the kind of cooling that you do to the sample, faster or slower. This is another example of how the metallography helps us to understand the way that you use to cool the sample. In this table, we have the annealing temperature and the time that was held the sample on heating. For example, a smaller times 15 for the sample W414, this one, or W714, this one. You can see some sizes, small grains in some cases. And for long times, for example, the sample A7 300 minutes, look, the size of the grain. It's clear that these grains are bigger than these ones. This sample was annealed in 15 minutes, and this sample, the A7 300, was annealed in 5 hours. So what kind of physical or mechanical characteristics are improved for this sample? The ductility. Bigger the grain, more ductile the material. And in short times of annealing or tempering, also you can say that a short annealing is a tempering. The grain is so small. And here is improved the hardness in sacrifice of fragility. Well, in steel, the process always starts with the austenite, always, and after cooling pass to other structures. For example, if you anneal a sample, the grain boundaries diffuse into another's and can disappear. But if you quench a sample, the boundaries are retained, small grains. And remember that in tempering you have two sections, the austenizing and the austempering. In annealing, just heat and cool slowly. But in tempering, you have two sections. Maintain the temperature in austenizing, and then, after quenching, maintain the temperature in austempering, around 350 and 400 Celsius. No matter the time, but always between 350 and 400 Celsius. Retain and let the material develop the next phases. What if you don't have steel? If you retain the annealing very long time, for example 30 hours, more than 1 day, if you increase the annealing temperature, a new structure, the spheroidite or spheroidite, appears. The spheroidite or spheroidite looks like here in SEM like small balls, small round particles. These materials are very soft, so soft. The sweet steel and another material that develop spheroidite are very soft. Well, what occurs for another materials? For example, this is a glass. The glass also have the phases that characterize the metals. Not only the metals that have this situation. At fixed composition, if you quench and you increase the time, you can pass from one crystalline structure into another. So if you draw the speed of cooling and the time that you hold this temperature, you can draw a path that follows the structures that you are creating. In glasses, for example, at hot temperatures close to the melting point, the glass is like a rubber. It's very elastic, very elastic. If you quench the glass, you pass through a viscous liquid state, and when you touch this line, the vitrification line, you obtain the solid glass. But what if you cool very slowly the glass? So you follow this line C1, C2, you don't obtain immediately the solid glass. You obtain a sol gel glass. Sol gel is a kind of structure when the glass is more or less more crystalline than the simple solid glass. Remember the concept of ceramic glass. It's also possible to obtain metallic glasses in that way. And what about the other? For example, if you want glass with small grains, small grains in the regions that are not glass, in the region partially devitrified, in the regions partially crystallized. So a tempering in glasses create tempered glasses. Small grains, very strong, very resistant to some stresses. But it's also possible to make an annealing for the glasses, erase some stresses, increase the grain size, and obtain more taller glasses, glasses that can withstand more stresses. This is an example of how also in thermal treatments we can use nanomaterials. For example, here bainite, that is a mixture of martensite perlite, is developed after several days of annealing at this temperature. Look, that is close to the austempering region. So the nanobainitic steel has a good combination of strength, ductility, and toughness for some specific appliances. Any structure in that kind of materials is always a nanostructure. Look at the ruler, 2 microns. Well, at this point, what do you understand about the thermal treatments and the relation between time, temperature, and transformation? I need to verify that you understand the concept. So please, after the end of the session, 2 p.m., send in groups of no more than 2 or 3 people a map, a mind map. Remember the rubric for mind maps. Very colorful. I need to verify that you understand the concept. Include figures, images that accompany the texts. This is only an example. The concept that I want to verify in you is the existence of different phases in time temperature transformation or cooling processes. What kind of thermal processes? Annealing or tempering. Annealing and tempering follow different paths. The cooling is what differentiates tempering and annealing, and the cooling rate, the time of cooling, and how much time you hold the temperature after different coolings is what create different phases. Remember that these processes can be developed in over any material: metals, ceramics, glasses, and polymers. In most of the cases, this stress the material, but especially in metals, create new phases, and these new phases are of interest for mechanical properties. Please make your questions. I will create a WhatsApp group to receive your questions along the class and other questions after class by email. Please join to the platform Edmodo, this one. This is an example. The code for you is very different from others. Remember to sign only in your group, not in others. I have the group of materials, so join only to your group. Verify what's the number of your group, 2, 3, or 4, and answer this post with your map. Please send me an image, picture, file, PDF, or as you develop the map as possible. Well, thank you very much, and see you in the next session. We will develop exercises doing